Okay, good morning, everybody. My name is Yapin Dan, and I'm faculty member at the University of Michigan Shanghai Jiao Tong University Joint Institute at Shanghai Jiao Tong University, Shanghai, China. Today, I'm going to present the device principle of low-dimensional, high-gain phototransistors. Photoconductors is the simplest devices. It is actually made of a semiconductor with two electrodes in ohmic contact. But this sort of device have extremely high gain. In particular, for low-dimensional devices, the gain can be even higher. This photo gain is defined as the gain in quantum efficiency. That means the number of carriers collected divided by the number of photons incident on the semiconductors. Okay. The classical theory was derived in 1956. Is actually following this definition, we can write as a number of photo access carriers as photo current divided by the unit of charge, and then divided by the light intensity divided by the h bar times omega. Okay. And then we can rewrite this expression as a photocurrent and then the light illumination and generation. And further, this equation can be simplified by assume the delta n equal to delta p, that's the excess electrons equal to excess holes. That makes sense because one photon will generate one electron and one hole. And according to semiconductor physics, we know that excess carrier concentration will equal to the generation rate times the minority carrier recombination lifetime. So that means delta n equal to g times tau. And we plug this equation back into this equation. The equation can be further simplified as tau as a minority carrier recombination lifetime divided by the tau transit time times 1 plus mu n mu p divided by mu n. That's excess carrier mobility ratio. This ratio cannot be, generally it's not going to be very big. For example, for silicon, the mu p is actually a third of mu n. So this mu p divided by mu n, that equal to 1/3. So the term in this bracket will not be big. Okay. So the dominant gain will be coming from the minority carrier lifetime divided by the transit time. So that means what? A photoconductor intrinsically will have a high gain as long as the device made it very short, because the shorter, then the transit time will become shorter. So the transit time defined as the excess carrier transport from one side of electrons across the semiconductor to the other electrode. So this theory is written in textbook. For example, the Semiconductor Physics and Devices Basic Principle is edited by Donald Neiman. So the first edition, page 634, that is written this equation. This equation is exactly what we derived. Another famous textbook, like Physics of Semiconductor Devices, is edited by Siemens Z. And on page 669, that equation is also same equation, but written in a different format, because the transit time they express as the transit time for electrons and transit time for holes, because their mobility is different. So the transit time will be different. Rest of the term is the same. So the in terms of device model, this can be explained as when the photon generate electron hole pairs. Okay, then one of the carriers will be trapped by surface states, for example, for low-dimensional devices. The other carrier circulate in the circuits many times before. So when the device makes shorter, makes smaller, so the transit time will be faster. Will be faster, so the gain will be higher. That's this is called recycling the gain model. But in 1984, Japanese scientists actually carefully investigated the parameters in this theory. What they find is, for example, they investigate a photoconductor made of gallium arsenide thin film, and the whole is the minority carrier lifetime, which is about 10 to minus 8 to 10 to minus 10 in this range, while the transient time for their detector, there is about 10 to minus 9. So the gain will be, by this theory, the gain would be not more than 10. But in the experimental results, they actually measure the gain as high as 10 to minus 4, 10 to 4 to 10 to 5. So it's clear this model cannot explain the experimental results, either for the value of the gain or for its dependence of the photon flux intensity. What does that mean? That means in experiments, the scientists is often observed that the photon flux, as you increase the photon flux, the gain, the photo gain actually will quickly drop. This phenomenon cannot explain by the classical theory. So in order to explain away this, the classical theory, the inconsistency of the classical theory and experimental results, so later on, scientists, engineers, they actually replace this minority carrier recombination lifetime with the transient for transient time. For the daytime, they use 90% of the magnitude of photocurrent, and then drop to 10% of the total photocurrent. That time is a delay time actually in circuits. So they plug this number into the original equation, the minority carrier lifetime, then looks at everything is not that different. So because of that, this theory is still widely accepted by the research community. So even today, in very often, scientists and engineers cited this equation to explain their experimental results. For example, the paper in 2006 and in Nanoletter, they're using this equation, and another paper in Nature Nanotechnology, they are also using this equation, the classical equation, to explain their experimental results. In this talk, I'm gonna divided my talk into three parts. The first part is a photoconductor intrinsically has no gain, and the second, we will derive the explicit analytical photogain, and the last, we're going to derive the analytical transient photoresponses. So first, we come to the first part. A semiconductor in contact with two metal under uniform light illumination, and no excess carrier will be generated in the metal. Okay. But an excess carrier will be generated in the semiconductor. For the sake of continuity, so the excess carrier will be in the semiconductor will not be uniformly distributed because of the metal semiconductor confinement. Due to the non-uniform distribution of the excess carrier in the semiconductors, under the electric field, the excess carrier will tilt. So the distribution will change. So the analytical expression can be found by solving the continuity equation with proper boundary condition. And this is what we find, the expression. And this expression, we also perform the numerical simulations using commercial device simulation software. We find that the continuity equation results is actually close to the simulation results. And they're not uniformly distributed. And the excess carrier will be pinched to zero at the metal semiconductor interface, and under light illumination, the excess carrier will be tilted and redistributed. And that means what? That means in the classical theory, we assume that delta n equal to g times tau is not valid for real semiconductor metal device because of the semiconductor metal boundary confinement. So the excess carrier will actually not only spatially is a function of space, but also a function of the voltage. And because of that reason, so we can actually find that photo current following the continuity equation is actually will be saturated. But for the classical theory, that is a linearly increase because there's no metal semiconductor boundary confinement. And based on this, we can also find the gain will be very different from the classical theory. If the majority carrier mobility is smaller than the minority carrier mobility, so the gain will be never higher than 1. If the mobility are equal, the gain will be approaching to 1, but never exceed 1. If the majority carrier mobility is larger than the minority carrier, so in that case, indeed, the gain will be larger than 1, but it will not higher than this 2 ratio. So that cannot be explained the high gain observed in experiments. But indeed, in the experiments, the high gain is indeed observed in the experiments. How can you explain that? So in that case, where is the gain coming from? That's a big question. So in order to explain the gain equation, we actually perform the photo Hall measurements inside on the nanowires. We use this B and C for 4 probe measurements, and we use C and E to calculate the Hall voltage. So what we find is this. So first, we measure the IV curve for nanowires. Okay, so nanowires are most linear when you change nanowire width. Okay, unless the nanowire width lower than certain value. So what we find over here is as we decrease nanowire width, the conductance or the current at a constant voltage is actually decreasing, okay, until they hit a value around 60 nanometer. And after that, after the 6 nanometer, and as you linearly decrease nanowire width, the current actually will exponentially drop. That means what? That means the nanowire has surface charge, surface states and surface charge. And then they will form surface depletion region. And so that caused the energy band were bending down near the interface for a p-type semiconductor. And then we performed the photo Hall measurements on this device. Okay. Photo Hall measurements is this equation. You have delta P minus the excess majority carrier minus the excess minority carrier times this mu n squared divided by mu p squared. That's from Hall measurements. And for photoconductors measurements, because the electron holes are both contributed to photoconductivity, so we can measure this mu delta p plus mu n divided by mu p plus times delta n. And surprisingly, the results of these 2 equations are actually almost the same. Almost the same, although they have this side is plus, the other side is minus. The only possible explanation is the delta n is much, much smaller than delta p. So delta n can be ignored. Okay, so that means inside this channel, the delta n are much, much larger than the delta p. That makes sense because under light illumination, the excess carrier will be separated by the depletion region and cause the hole actually accumulate inside the channel. This is p-type semiconductor, so the majority carrier will be accumulated inside the channel, and the electrons will be separated by the depletion region and accumulated near the surface. So the photocurrent contributed mostly by the excess majority carrier, not the excess minority carriers. So that means also one photon will create 1 electron and 1 holes, but the excess carriers contributed to the conductivity are mostly by the majority excess carrier, not by the minority excess carriers. So that means that delta n are not equal to delta p. Due to that reason, so we cannot simplify this equation. Okay. As we show later, we see this. This is the gain is dominantly coming from the delta p divided by delta n. That's the excess majority carrier divided by excess minority carrier. It's dominated by this term that we define as G prime. Okay. But even we have this equation, and the G prime is dominant factor generate the gain observed in the experiments, but this equation is implicit equation because most experimental results we measure the photo current as a function of light intensity and the photo gain as a function of light intensity. And this equation has nothing to do with this light intensity equation. So it is explicit. It cannot be used for fitting the experimental results. Now, what we need to do next, what we are going to do is we are going to find the explicit analytical photo gain equation. So as we find previously, the light illumination was separated by the electric field and will cause the accumulation of excess carrier in the channel, excess minority carrier near the interface, near the surface. This charge separation will create a positive bias on this depletion region that will narrow down the depletion region. And in the experiments, by perform photo Hall measurements, we can actually see this depletion region actually will change around 32 nanometer under light illumination, and that will change to around 28 nanometers, narrow down. And from the photocurrent, photoconductance, we can calculate the number of the excess carriers is dominated by the majority excess carriers, right? Before we consider the depletion region change, and what we find is nominal. If we just ignore the depletion region change, then we find the excess carrier concentration will increase around 10 to 17, is relatively high number. But if we consider the excess carrier expansion and then the actual excess carrier change inside the depletion region can be ignored, is almost zero. That means the photoconductance is dominantly contributed by the channel width extension, not by the actual excess carrier increase. So due to that reason, we can model this nanowire high gain photoconductor as a sort of like a phototransistor. It has this is a resistor. It has a channel width, and the channel width is actually modulated by the light illumination. It's like a phototransistor. So that will the light illumination will narrow down the depletion region, widen the channel width. So what we find over here is light illumination will cause this depletion region narrow down, and as a result of that, the depletion region, the channel width will become larger. So based on this model, we can find the photocurrent light illumination. We can generate separated by the depletion region. You will create a forward photocurrent. Forward photocurrent will create a forward photo voltage. That photo voltage will create a forward current that will cancel out this reversed photocurrent. Okay, reversed photocurrent. So based on this, we can actually rewrite this equation. We find the photo voltage dependence of the light intensity, the generation rate, and based on from there we can find the photocurrent as a function of the light intensity, and that will actually following a log scale. So by doing that, we can fit the photocurrent as function of light intensity perfectly, and also we can find the photo gain as function of light intensity, and we fit the experimental results very well also. And based on this fitting, we can actually find a lot of parameters. In particular, we can find the excess minority carrier recombination lifetime and the surface recombination velocity. And since we have this minority recombination lifetime, we can plug this equation back to here, and the maximum equation, the gain, will actually reach into over here. So these equations are all based on the physical parameters of the nanowire, and that is equal to 1.45 times 10 to 6 times minority carrier recombination lifetime divided by the transit time. And because we find this minority carrier recombination lifetime, that's around tens of nanoseconds. The transit time is also similar scale. So if we call, according to the classical theory, that is following this theory, the gain will be not more than 24. And our actual gain can be as high as 1.8 times 10 to 6. Okay, for one of the nanowires. So for the black nanowires, close to 10 to 7. So this is in line with our experimental observation, but the classical theory cannot explain this. It's very different. Now let's come to the last part of this theory over here is analytical transit responses. Now, based on the same model, because the light illumination is actually cause the depletion region narrow down and the channel width expand. So based on this theory, we can derive the following transit process. So light illumination will create a reverse photocurrent, and that reverse photocurrent cause the excess carrier accumulate in this region. That will create a forward photo voltage inside the depletion region, and then that will narrow down the depletion region and create a forward photocurrent. And if there are surface states, then the surface states will trap or detrap the photo excess carriers under the light illumination, on-off light illumination. And in the end, we find that the four transits, that is, can be written as this expression, these two expressions over here. They have to divide in two sections. So if the light illumination, if the track density is relatively small, so then the transit time was dominated by the first expression following this expression over here. If you have large trap states, so then you divide it by two sections. The first part will be divided by equation 8a, and for the second part, then the tail is dominated by the emission of the excess carriers. And for the depletion region relaxation, so is following this equation is not a simple exponential term. Characteristic delay time is tau c it can be expressed over here. Okay. So experimentally, we also we find that our equation can fit experimental results very well, depending on different light intensity, and the tail can be also fit a simple exponential term, and with these results. Okay. From the fitting, we find the trap lifetime is relatively long, is around several seconds, and then the surface depletion region relaxation is about milliseconds. And based on the milliseconds governed by this equation, this tau zero can actually estimate from the previous steady state fitting results. And if you plug this steady state tau zero back into this equation, we find that the tau c should be a constant of the light intensity following this equation. It's pretty close to the transit fitting results. And based on the maximum gain equation, we find the maximum gain can be expressed over here. Based on the 4 transit time, we find what? The 4 transit time, we find this equation, and then the 3D band width can be written to 1 over tau 2 pi times tau c. And we plug this equation back to over here, we find this equation over here. So the gain bandwidth product over here, the gain bandwidth product can be written as gain maximum times the 3D bandwidth is written over here with this equation. The last part is P injunction, the gain bandwidth products. And this equation over here will be approached to 1, but will not be higher than 1. The alpha is absorption ratio, okay, normally less than 1. So in overall, what that means? That means that the high gain photoresistors or photoconductors, their gain bandwidth products will be never higher than the gain bandwidth product of standard PIN photodetectors. Okay. But even though they are not be higher than that, but this is still meaning this high gain nanowire photoconductors still have useful because their gain can be designed and can be tuned, and you can design very high sensitive photoresistors for low frequency application. So as conclusion is a class we find is the classical gain theory is derived on two misplaced assumptions, and we derived the explicit gain equation for single crystal photoconductors. And then the photogain originated from the channel width modulation by the light illumination, like a gate. Okay, that's why we call this high gain photoconductor as a phototransistor. And we find the analytical transient response for these photoconductors or photogain, phototransistors. The gain bandwidth product is not larger than that of a regular PIN photodiode. But the gain and the bandwidth of this phototransistor can be designed by changing the doping surface charge, surface depletion region, doping concentration, nanowire width. So we can design this sort of nanowire, highly sensitive nanowire photo transistors for low frequency application. In the end, I'd like to thank my group member and funding agent. And thank you very much.